Okay, so for this question, whenever they said show that, so you have to write a statement first. So you will write in words, right? The gravitational force provides the centripetal force. But do write it in words, not just symbols like this. Then after that, you will write down the formula for gravitational force, which is G m over r squared equals to mv squared over r. So cancel one m, cancel one r, alright, and then you will bring the square root over, your square over becomes square root, so v equals to square root gm over r. So that's how you prove this part. Now next, for the kinetic energy, you remember the formula for kinetic energy is half mv squared. So you substitute the v from just now, which you remember was square root gm over r. So when you square it, you get g m over r. So you will get g m over 2r. So that's your answer. Now as for the gravitational potential energy, you can straight away use from your memory, the one you're supposed to have remembered. So gravitational potential energy is negative g m over r. So don't forget the negative, because all GPE values are negative. So after that, to find the total energy, you add up both. So you notice that they get negative g m over r plus g m over 2r. So if you were to factorize the 2r, then you will get negative g m over 2r. Alright, so that is your total energy. So you will notice that both the GPE, alright, both the GPE and the total energy will be negative, because your GPE is much bigger than your KE here. So when you add up both, your total energy will still be negative. And remember, the maximum energy is 0 at infinity. Now for this part, when they said the total energy of the satellite decreases, what happened to the radius of the orbit? Now the clue is, if you look at the total energy, right, remember the formula was negative gmm over 2r. So this is already a negative value. So if it decreases, will it get more negative or less negative? So we know that if it's a negative value and becomes smaller, that means it's going to get more negative. So to become more negative, the r here must decrease, because when this one drops, the whole value becomes more negative. So that's how you would answer it. So your answer would, you would say that the total energy is now more negative, so r decreases. Right, and then for the next part, the linear speed of the satellite. So they accept, right, your explanation if you use KE or or your speed, KE or your speed, because both equations, right, will tell you about the speed. So assuming that you're going to use the formula for your speed, so if you're going to use the formula for the speed, which is gm over r square root, so you can say when r decreases, v increases. Alright, but you can also quote the formula for KE if you want, which was KE equals to gmm over 2r. So you can say then r decreases, KE increases, so speed increases. Now for this question, there is this planet that is orbiting around the sun. So for you to define angular velocity, right, for 2 marks, so you can't just say angle turn through per unit time normally, because of the second mark here. So you will say angle or turn through by the radius per unit time. All right, so that's the full definition. So what is the relationship between omega and t? So remember, omega equals to 2 pi over t, right? Omega is 2 pi over period. Now for this one, to prove that t squared equals to CR cubed, this is actually Kepler's third law, because if you remember, t squared over r cubed is a constant. So t squared equals to constant times r cubed. So since in the previous question they gave you omega, and don't forget explain your working. So you put it in words, in a statement. You say gravitational force provides the centripetal force. Then you would say gmm over r squared equals to mr omega squared. Then you can cancel one of the m, but you can't cancel the r. So you will get gm over r cubed equals to omega squared. So the next step is to get rid of the omega. So you will still remember omega equals to 2 pi over period. So you substitute that inside, you get gm over r cubed equals to 4 pi squared over t squared. So that would give you, bring the t squared over, so you get t squared, and then you will get 4 pi squared over gm times r cubed. So this is your constant. So then you can write kr cubed. So that is actually Kepler's third law. Now, for the next part, they said use the expression part B to determine the value for Neptune. So you remember that t squared over r cubed is a constant, right? So what you can do is you can make use of the values here. So if this is a constant, alright, so then you can do the t squared over r cubed for the first planet equals to t squared over r cubed for the second planet. So remember the period for Venus, which is 0.615 squared over radius 1.08 cubed must be equals to t squared over r cubed for Neptune, which is t squared over 45 cubed. Now you don't have to change any of the units because both the years, right, which is the period and also the radius are the same unit. So this will be years, and then this will be 10 to the power 8 km, so they will cancel each other for the ratio, right? So these two were same units, these two will be the same units, all right? And you want the answer to be in years, so you don't have to convert. And then you will get the period in 1SF to be 165 years. Right, then after that, to find the linear speed of Venus in its orbit, since you already know the radius and the period, so you can use the standard formula V equals to 2 pi r over period. So the radius, substitute, which is 1.08. Now this is in kilometer per second, so you have to put the 10 to the power 8 there, all right, but you don't have to change to meter. And the period, if you remember, is 0.615 years, which you have to convert to seconds. So 0.615 years times 1 year is 365 days. Now you don't have to care about the leap year, all right, times 24 hours times 60 minutes times 60 seconds, all right, and that way you will get the linear speed, and that way you will get about 35.0 kilometers per second. Right, for this question, they want you to prove r cubed omega squared is a constant. So what do we do? Now, since this is a satellite, so it is a good idea to start from the formula of satellites, which is gravitational force provides the centripetal force inwards, because once again, you have explained your working. So gmm over r squared. Now, since they want your answer in omega, so it makes sense to use mr omega squared. So the next one you can do is you cancel 1m, then you bring the r squared over, then you get r cubed omega squared equals to gm, where this is your constant. All right, so that's what you want. Now for this part, since you want to find the mass of Mars, you may want to use what you just derived, which was r cubed omega squared is a constant, which is your gm. So what you can do is you can actually use the Phobos, the information from Phobos. So r for Phobos is given 9.39 times 10 to the power 6 cube times omega, which is 2 pi over 7.65. Now for this one, you have to convert it to seconds, because your what they call it, the mass is in SI, so you have to convert everything to SI. So G is 6.67 times 10 to the power negative 11, so times the mass, which is the mass of Mars. Then you should be able to get the mass of Mars, which will be m equals to 6.46 times 10 to the power of 23 kg. Now for the next part, to find the period of Deimos, you can either use back r cubed omega squared is a constant, or you can actually use the Kepler's third law if you want to. That's easier. So Kepler's third law will be t squared over r cubed is a constant. So t squared for Phobos is 7.65 square over 9.39 times 10 to the power of 6 cube t squared over r cubed for Phobos equals to t squared over r cubed for Deimos. So you want to find the period for Deimos, and this one radius will be 1.99 times 10 to the power 7 cube. Now in this one you don't have to convert any units because you want the answer to be in hours, and the period of Phobos is already in hours. So after calculating, you get the period as 23.6 hours. Right, the period of rotation of Mars about its axis is 24.6 hours, and Deimos is an equatorial orbit, same direction, orbiting same direction as the spin of Mars. Comment on the orbit of Deimos. Now, if you remember, right, geostationary satellites, they actually have this characteristic above the equator, orbiting same direction, and the period of orbit should be equals to the period of rotation, but they're not exactly the same though, but it's quite similar. So what can we say that there are two acceptable answers? Since this is quite similar and it does fulfill the other condition like equatorial orbit, orbiting in same direction, so you can say that Deimos is in an almost geostationary orbit around Mars. Or you can also say, now if the period of the Deimos, right, is shorter than the period of rotation, that means the satellite is actually moving faster, right, around Mars than the rotation of Mars itself. So if it's going to move faster than the rotation of Mars itself, so you will see, imagine you're standing on the surface of Mars. If you look at the moon Deimos, since it's moving slightly faster than the rotation, so you'll see the moon, right, slowly moving across the sky, because relatively it's slightly faster. So therefore you can also say Deimos is seen to move slowly across the sky. Right, for the next part, they want you to again show that the speed. So I already showed you in the previous question. So explain the working, say in words, gravitational force equals to centripetal force. So GMM over R squared equals to MV squared over R. Cancel 1M, 1R, and your V, you will get square root GM over R. Now for this one, they said determine in terms of the gravitational constant the speed of the stone at the distance x from the center of the planet, right? This is what they were talking about. Explain your working, and then you must also say that the stone here is initially at rest at infinity, so it travels towards the planet. So if it was at infinity, right, the GPE will be 0 and the KE is 0, because at rest means KE is 0, at infinity the GPE is 0. So as it comes towards the planet, it will lose GPE but it will gain KE, right? So you can use the conservation energy to actually find the speed V0. So it will be loss in GPE equals to gain in KE. So that so happens to be your explain your working part. So what's the loss in GPE at infinity is 0, so you minus the GPE at the surface, which is GMM over, now not surface, sorry, it's actually at the distance x, so this is x, so equals to, now the KE at that point is half mv squared minus the KE at infinity is 0. So that way, the 0 you can forget about it, then the minus or negative here becomes a positive. So then after that you can cancel 1m. Alright, then after you cancel 1m, you can get the value of the V0. So what is your V0 here? So V0 will be equals to 2gm over x square root. Alright, so that's what you want to prove. Now, the next part, they said that use your answer expression to explain whether this stone could enter a circular orbit. Now, if you remember the previous part that we did, the speed, right, of orbit, right, the one that we just derived in the earlier page was V equals to square root GM over R, where R was the radius of orbit. But if you notice, the speed of the stone when it reached this point here is square root 2 GM over X. Alright, so that means if you are talking about the distance X from the planet, the speed of orbit should be square root GM over X. But your speed is square root 2 GM over X. So can you see your speed here is higher than the speed of orbit? So what will happen if the stone enters too fast? then the centripetal force it requires cannot be supplied by your gravitational force. Is not enough. Your gravitational force is not enough to supply your centripetal force because it's too fast. So therefore, what you can say is, because you say use the answer and expression part A, so you must say that the speed of the stone is greater than the speed of orbit. All right, so that's 1 mark. So therefore, the stone, now what will happen to the stone? The planet will try to pull the stone towards itself, but it's not enough, right? The gravitational force. So it will spiral slowly out of orbit. So it will go further and further away. So you say the speed of the stone is greater than the speed of orbit. Therefore, the stone will slowly spiral out of orbit. Right, for the next part, they want you to show the KE of the satellite. Now, this is pretty similar to what we have done as well. So, explain your working. So, don't forget your standard one, gravitational force is equals to centripetal force inwards. So, you can start with GMM over R squared equals to MV squared over R. Now, why use MV squared over R? Because I got to use KE, right? KE is half MV squared. So, I want V, so not omega. So, I wouldn't use GMM over R squared equals to mr omega squared because I want V. So cancel one m, cancel one r, and your V, as usual, you get square root gm over r. Then ke half mv squared, so substitute the V inside there, and then you will get just gm over r after you square it, right? Square root, you cancel each other, so you get gmm over 2r. But because, right, they mentioned about specific terms, so you can replace, right, your small m here, all right, which mass of the satellite as ms. So this one will be ms. All right, and also the distance they mentioned, right, was distance radius x. So the orbit is x, so you can change this to x. So you will get the answer. So gmm over 2x, and don't forget this is the mass of the satellite. Okay, so this one also, if you want to, you can convert. So this is x, this is x, so you can cancel one of the x. This is the mass of the satellite, this is mass satellite. So initially it gets cancelled off, all right, but later on when you times back the m here, then the mass will appear back again, mass of the satellite. Now, what about the potential energy? So I told you this one you got to memorize only, nothing special. So the GPE is always negative gm mass of the satellite over x, because actually it's negative gmm over r. So I'm just replacing the symbol. So again, total energy just add up together. So remember your GPE is negative gmm s, this mass of satellite over x. And the KE was simply gmm mass of satellite over 2x. So therefore what you will get is negative gmm of the satellite over 2x. Alright, so that's the formula for your total energy. Next part, small resistive forces acting on the satellite causes the radius of the circular orbit to change. Use our answer to state for the satellite whether each of the following quantities increases, decreases, or remain constant. Now imagine it's undergoing a satellite orbit. After that, some resistive forces, perhaps it collides with some space debris, which causes it to slow down. All right. So what will happen is when it slows down, your KE will drop definitely because resistive force will slow it down. So the total energy will definitely drop because you slow down. So your answer here would be decreases. All right. You can say in words decreases. But what happens to the radius of orbit then? Now, remember we said, right, if let's say you slow down, your centripetal force will actually be smaller. And for perfect satellite, your gravitational force, gmm over r squared, must provide exactly, or rather must be used up completely for your centripetal force. The moment you slow down, when the centripetal force drops, you will have excess gravitational force. So that causes you to start spiraling down towards the planet, right? Not so therefore the radius will start to drop, okay, because the gravitational force is bigger than the centripetal force now. So the leftover gravitational force, so that pulls it inwards, so that it comes spiral. So what happened to the PE at that time? So remember your GPE, right, was negative gmm over r. So as your r starts to drop, right, you notice that your GPE gets more negative. That means it decreases because you're actually moving towards the planet. So a satellite moves nearer and nearer towards the planet, so you lose GPE. So the potential energy will decrease. But what happened to the KE? Now, you must understand the total energy, right after meeting with the resistive force will drop. But this new total energy must be conserved, assuming there's no more resistive force after that. Right, so the resistive force causes it to drop. Then after that, with this new total energy, as it starts to spiral inwards towards the planet, the total energy is conserved. So since your GPE is going to drop, your GPE must be converted into KE. So your KE will start to increase. So it means as you spiral down towards the planet, you'll go faster and faster. Now, for this question, they want you to find the change in kinetic energy when it moves from x is 0.1 to x equals to 1.2. So what you have to do is you go to read from the graph what are your values. So how do we actually find the what do you call it, the KE, right? So think about this, right? So this is actually the graph of potential versus the distance x, right, from the star A. And the point P is actually lies on the line joining. So as the distance x, right, increases from here, all right, when you move from 0.1 to 1.2, okay, which is here, do you realize that the potential was here, then after that is here? So that means it's getting more negative. That means the potential drops. But how do I find the KE? So again, there is a conservation of energy here. So you'll be lost in GPE equals to gain in KE. Now, unfortunately, your graph is potential, right? Not potential energy. So what do we do? So remember, potential is also can be found by potential energy divided by mass. So potential energy is mass times potential. So since I want change in GPE, which is delta U, I'll get mass times change in potential. So I can use the graph here to find the potential. And then after that, I find the difference. Then I times the mass. So now, mass of what? You must times the mass of the rock, which is a test mass here. And you find the change in GPE of the rock. So what you're going to have here is loss in GPE will be mass times change in potential. So if you can read right from the graph, the potential at 0.1 is negative 10. The potential at 1.2 is negative 14. So when you say loss in GPE, so you have to take the bigger minus the smaller, right? So let me just write nicely. So this one will be m, which is the mass of the stone. Change in potential, so the bigger potential, which is negative 10, right, minus the lower potential, which is negative 14, right? So basically you're going to get 4, right? Don't forget there's a power of 10 to the power 8 there, so don't forget the 10 to the power 8. So that will be equals to gain in KE, which is delta EK. Now you don't need to find the speed, so you can leave it like this. So you substitute the mass here as 180, then this will be 4 times 10 to the power 8. That's how you find your change in KE. And if you calculate, you will get as 7.2 times 10 to the power 10 joules. Now, is it an increase, right, or decrease? State whether this change is an increase or a decrease. So since your GPE is decreasing, so your KE is an increase. All right, so that's your answer. Now, for this next part, it's a bit tricky. They want you to find the minimum speed so that the rock reaches the point of x equals to 1.2. Now, how is this different from the previous part, right? Some people ask me, since I already found the change in KE, can I just use half mv squared equals to the value you just calculated, right now? Seems logical, okay, but there's a trick involved here. Here we're talking about the minimum speed. Now, what does it minimum speed mean now? How do I represent these 2 points, right? So imagine you are standing on a cliff, right? Imagine you're standing on a cliff, all right? So you have a certain value of GPE. So when you throw the ball up, all right, your GPE is going to increase. So that will represent this part. Then after that, when it falls to here, so it represents it falls past the cliff, then maybe into the sea. So therefore, the GPE at this 1.2 is somewhere in the sea here. So you will notice that they want you to find the minimum speed. You need to throw this to reach here. But to reach here, right, you don't have to give it speed all the way from here to here. You just have to give it enough speed to reach the highest point. Once you give it the speed to reach the highest point, it will stop for a while, then it will fall by itself. So you must give it enough speed to reach the highest point. You don't need to go all the way from here to here. So previously, just now, we were just finding the difference in GPE between these 2 points, all right, in the previous part, and what will be the change in KE if you move from here to here lah, all right. So here I'm not finding the change in GPE from here to here or the change in KE from here to here. I just want to find the speed to reach this point, the highest point. So all you have to do is you find the GPE at this point, you find the GPE at the highest point, all right, and the difference in GPE will be the difference in KE. That means as you move up from here to here, your gain in GPE will be equals to your loss in KE. So from that, you can find the speed that you need to throw it the highest point. After that, it will fall by itself. All right, so you can start off by saying loss in KE equals to gain in GPE. So half mv squared, which is the speed that we are going to calculate the minimum speed. So once you reach your highest point, the KE will be 0. Now gain in GPE, be careful though, this is potential. You still have to convert to potential energy. But no worries, because we know that mass times potential is GPE. So the mass times the change in potential will be your change in GPE. So what is the change in potential? Now if you read this value accurately, because 10 boxes is 4, 1 box is 0.4. And if you were to read it, I'll just show you this. You will get a value of negative 4.4. So therefore, if this value is negative 4.4 and this value was negative 10, so the difference will be just either you take the higher one, negative 4.4 minus negative 10, or you just find the difference in magnitude. So 10 minus 4.4 also can, doesn't matter. So 10 minus 4.4 will give you 5.6. So if you're lazy, you can just put that 5.6. Don't forget the 10 to the power of 8. All right, so you can cancel 1m and then you can find the speed. So if you calculate, you get your speed as 3.3 times 10 to the power of 4 meters per second.